to another episode of Mr. Avila Physics. Today we're going to talk about impulse and collisions. Collisions are very common during everyday life, right? If you play sports, a tennis racket hitting a ball, a bat hitting a baseball, right? Somebody kicking a soccer ball. All those are examples of collisions, right? A hammer hitting a nail, a person jumping on the ground, someone knocking on the door. All those are examples of collisions. Now, when a collision occurs, usually the forces between the two objects involved are far stronger than anything external that could be happening to the system. So when a collision occurs, we can ignore other forces that are external to the contact of the two objects. Things like gravity, friction, air resistance, anything like that can be ignored at the collision point. Not the time leading to the collision or after the collision, but when the contact occurs. So when a collision occurs, at the point of contact, at the time of contact, the force that each object exerts on another jumps from 0 to a certain level very, very fast. Okay, and then when the contact stops, the force returns to 0. So what we have is once contact occurs at a certain time, the force jumps very quickly to a high level, and then once contact stops, the force goes back to 0, right? So the force only happens for a very short period of time, and it's usually very strong, okay? This is the point where the ball is reaching the racket, right? Maximum force right here, and over here, for example, is when the ball leaves the racket, already having applied a force. Now, in a previous video, we talked about how Newton's second law relates to momentum. So we can see it again here, right? We learned that the force applied to an object is equal to the rate of change of momentum. Now, if I multiply both sides of the equations by delta t, I obtain this mid part of the equation. And this quantity right here, this is known as impulse. So the impulse given to an object by another object is equal to the average force if it's not constant. So it should be average force multiplied by the amount of time that the two objects are in contact with each other. So I can rewrite this equation as impulse equals F delta t, or I can also say that impulse is equal to the change in momentum. Either one of this works perfectly well, right? There are both definitions of impulse. So we can see that change in momentum is equal to impulse. So sometimes talking about impulse is better than talking about the change in momentum, especially when there's a large force in a short amount of time, like a bat hitting a baseball. So the force is not generally constant. It kind of increases because the baseball kind of deforms a little bit and then forms back as it leaves the bat. Same thing with a tennis racket and a tennis ball. The tennis ball flattens a little bit and then reaches its normal form as it leaves the racket. So if I have a graph of force over time, then I can find the impulse by finding the area underneath the graph. So in a force versus time graph, this area right here, this is known as impulse. All right, so talking about objects colliding, we have two types of collisions. we have elastic collisions and inelastic collisions. When dealing with an elastic collision, right, then we know that total momentum is conserved based on the conservation of momentum, but in an elastic collision, there are no energy losses. So in an elastic collision or perfectly elastic collision, then momentum and kinetic energy are conserved. Okay. Now, we learned in previous videos that the total energy of an object, including losses, is always conserved, but in an elastic collision or perfectly elastic collision, then there's no energy lost. So that means that besides the total energy being conserved, also kinetic energy is conserved. This is very important to know. So in an elastic collision, both momentum and kinetic energy, they're both conserved. Now, how does this help? Well, let's see. If we have a perfectly elastic collision, then we know that the momentum is conserved, and we know that kinetic energy is also conserved. Now from here, we can do some simplification here, right? So for example, I could say MA times VA minus VA prime is equal to MB BV prime minus VV, right? And then from this right here, from this equation right here, I can cancel the 1/2 and then do something similar. I can say MA, and then this is VA squared minus VA prime squared, and this is equal to MB BB prime squared minus BV squared. Okay, and from here we see here that we have a difference of squares, so I can say that MA times VA minus VA prime times VA plus VA prime is equal to MV times VV prime minus VV times VV prime plus VV. Now we're going to see if we can simplify this a little bit. So for example, I can say here that MA is equal to MB times VV minus VV prime divided by VA minus VA prime. And take this value and substitute it into that equation there. So then if I substitute, then I can say, all right, so I'm going to make some room over here. MV VV minus VV prime times VA minus VA prime VA plus VA prime divided by VA minus VA minus VA prime is equal to MB VV prime minus VV times VV plus VV prime plus VB. From here we can cancel MB. We can cancel, what else can we cancel? VB minus VB prime. And we end up with this equation right here. VA plus VA prime is equal to VB plus VB prime. And this is a good equation to know right, in perfectly elastic collisions. I mean, this gives us a way to relating the velocities of both objects just before the collision and just after the collision. So, if we take this example, a Wheeler ball of mass m moving with speed va collides head-on, that is face to face, okay, with ball b of equal mass. What are the speeds of both balls after the collision if we assume an elastic collision? All right, pause the video here, take a couple of minutes, and see if you can solve this example. Okay, welcome back. So we have ball A moving this direction, ball B moving this direction. They'll collide, and then they'll probably move in opposite directions. Now we know that momentum is conserved before and after the collision, so ma va plus mv vv is going to be equal to ma va prime plus mv bv prime. We know the balls are identical, so the masses cancel, and we are left with va plus bv. This is equal to va prime plus bv prime. Now, we also know that kinetic energy is conserved. And from what we just saw, I know that va plus va prime is going to be equal to bv prime plus bv. If I arrange this equation a little bit, I get, this is kinetic energy conservation, and this is momentum conservation. If I rearrange this, I can get something like va minus bv is equal to bv prime minus va prime. Now, if I add the momentum of conservation equation right here, va plus bv equals va prime plus bv prime. If I add these two, this cancels, and this cancels. So I end up with 2va is equal to 2bp prime. I end up with va is equal to bp prime. So that means that after the collision, each ball went in the opposite direction with the velocity that the previous ball had. So after they collided, ball B is going to move in the opposite direction with va, and when BA collides, it's going to move in the opposite direction with velocity BP. As we can see here in the solution from your textbook. All right, now we're going to talk about inelastic collisions. We saw earlier that when two objects collide, the total momentum is conserved. But in perfectly elastic collisions, kinetic energy is also conserved. When kinetic energy is not conserved, then a collision is called inelastic. In reality, in real world physics, most of the collisions are inelastic. It's going to be very, very hard for two objects to collide and conserve all their kinetic energy. But in textbook physics, kinetic energy is conserved in elastic collisions. So when kinetic energy is not conserved, the collision is inelastic. Right? So some of this energy gets transformed into thermal energy or potential energy or deformation energy when the object deforms. So usually, well, not usually, always, the kinetic energy after the collision is going to be less than before the collision. Now, this is the total energy, not a single object's energy. The total energy, the total kinetic energy of both objects before the collision is going to be greater than the total kinetic energy of both objects after the collision in an inelastic collision. If during the collision the two objects stick together and move as one, then we have a perfectly inelastic or completely inelastic collision. All right, so like in all collisions, momentum and total energy are conserved. Okay. All right, before we do this next example, just a quick summary. Elastic or perfectly elastic collisions, momentum and kinetic energy and total energy are conserved. In inelastic collisions, momentum and total energy are conserved. In perfectly or completely inelastic collisions, the objects stick together and move together as one. All right, let's look at this next example. A ballistic pendulum is a device to measure the speed of a projectile, such as a bullet. So what happens is the object is traveling at an unknown speed, hits the pendulum, gets embedded inside the pendulum. Embedded means stuck. And then the two objects, the pendulum and the bullet, move together as one in a pendulum form, like this. And eventually, the pendulum stops at a certain height, making a certain angle with the vertical. Okay? All right, so the question here is find the relationship between the initial horizontal speed of the projectile and the maximum height reached by the pendulum. Okay? All right, so what we have here is, let's see if we have, okay. So what we have here is a bullet traveling, and then it's gonna hit, excuse my drawing, it's gonna hit a pendulum, and then both the bullet and the pendulum are gonna move up to a certain height, right? And this height is h. And this bullet is gonna strike the block at a certain velocity. So let's see what we have now. As we can see here, the bullet gets stuck in the block. So this is a completely inelastic collision, which means that the two objects move together at the same speed. So if I start this problem with conservation of momentum, then I'm going to go with m mass bullet, velocity bullet, plus mass block, velocity block is going to be equal to mass bullet plus mass block times a certain velocity. Now I know that initially this is 0. So I have that mass bullet times the velocity bullet before the collision is going to be equal to the total mass times the velocity after the collision. So here I need more information, right? Because I cannot have an relationship between h and v before the collision. So I gotta find a value for this velocity, the velocity after the collision, in terms of h. And in order to do that, I'm going to remember that I know that in all collisions, energy is conserved. So that means that the total energy before the collision is equal to the total energy after the collision. So if I consider this my point 1 and this my point 2, then I can find out that the total energy at point 1 has to be equal to the total energy at point 2. Now, right after the collision, the block and the bullet begin to move together, right? So that's going to be kinetic energy. And then right after it moves and they reach a certain height, then that's going to have potential energy. So all the kinetic energy of both the block and the bullet is going to be transformed to potential energy, which means that 1/2 v prime squared, because this is the velocity after they collide, is going to be equal to mgh. Now keep in mind that this mass is the total mass bullet plus mass block. But it doesn't really matter because right here it cancels. So here I can see that v prime, the velocity after the collision, is going to be equal to the square root of 2gh. So I take this value and I substitute it in there, which means that once I combine this, I'm going to have mass bullet, velocity of bullet is going to be equal to total mass bullet plus mass block, times v prime, which is going to be equal to the square root of 2gh. So the velocity of the bullet just before it collides is going to be equal to mass of bullet plus mass of block divided by mass of bullet times the square root of 2gh. And this would be the relationship between velocity and height. Okay. As we can see here, the solution from your textbook, we had the same answer as they did here. All right. Thank you all for watching, and see you next time.